This is Chapter 2, the Chemistry of Biology for your microbiology class. Chemistry, depending on your background, can be quite daunting, but I am here to help you understand it and encourage you to ask questions as they come up. If you've already taken Anatomy 1, this is going to be a lot of review of that and then building on that knowledge from that chemistry and biochemistry that was covered. So matter is what occupies space and has mass. It's most things you think of. And an atom is a tiny particle that can't be broken down into smaller substances without losing its property. So it's what makes up matter. Now there's subatomic particles, sub meaning below. So below the size of an atom, smaller than an atom, are protons, neutrons, and electrons. Now, these are smaller substances, but if you remove them or add more to the atom, it does change its properties. So an atom is our lowest level for matter. Let's talk about those subatomic particles. Protons, shown with a symbol with a P with a positive, because they are positively charged, and these are found in the nucleus of the atom, kind of the central portion of the atom. Along with the protons in the nucleus are the neutrons, which don't have a charge, so they are shown with an N to the 0 symbol. So protons and neutrons are both found in the nucleus, and together they make up the mass, the atomic weight of the atom for atoms here on Earth. Okay, so protons and neutrons are found in the nucleus, and it's the nucleus that's the bulk of the atom, and that's why when you calculate atomic mass, you'll be adding the protons and the neutrons together. Electrons, which are found surrounding the nucleus, constantly moving, orbiting, are negatively charged, and that's why their symbol is an E with a negative. So here is this very simple atom, the hydrogen, and you can see that in its shell, orbiting around the nucleus at the center, you see one hydrogen electron. That's this little gray thing out here. And then at the center, we have one proton. Now, what charge do electrons have? And what charge do protons have? And so for atoms on our periodic table, these numbers are always going to match. The positives, the protons, which are positive, are always going to be the same as the number of electrons, which are negative, okay? So protons here in the nucleus, electrons in the shell. Now carbon, a little bit more complex, has 6 protons in the nucleus. You can see the nucleus here with the protons there. And so if we have 6 positive subatomic particles, we're going to have how many negative? 6. So you can see them orbiting here. There's 6 of these electrons. Now, in this atom, there is something called the octet rule. And it states that only the first shell, the first electron level, can hold 2 electrons, and the next level can hold, it's called octet rule. Oct means 8. So the next shell can hold 8 electrons. In fact, carbon is never going to be found by itself because it needs 8 electrons in its outermost shell to become stable. So carbon is an unstable atom by itself, which we would call reactive, and hydrogen, the same thing. Now, how many shells does hydrogen have? Just 1. And how many electrons? What's the maximum number of electrons that can be on that first shell? There can be 2. So remember, the first shell can hold 2. How many can the second shell hold? 8. Well, hydrogen only has one. So is its shell complete? No. So it's also reactive. It's also an unstable atom by itself. And so hydrogen and carbon will do chemical reactions with other atoms to become stable, to fill these outer shells of their atoms. So what is an element? It's an atom with a characteristic atomic structure, and it has predictable chemical behavior. Now, there are things called isotopes. Iso means same. So they're the same element, but they have a different number of neutrons, so they behave a little bit different. They're a different form. So, for example, this carbon is C12. It has 6 protons and 6 neutrons in the nucleus, but there's C14, and so that would be 6 protons and 8 neutrons would form that isotope of C12. So these radioactive isotopes have unstable nuclei that are going to spontaneously, that means by themselves, release energy in the form of radiation. And these are used in research and medical applications. For example, that C14 I mentioned is what we use for carbon dating, really old things that were once alive. We're talking thousands and thousands and thousands of years ago. We can look at how much C14 is still in those tissues and get a relative idea of how long ago those things were alive. So here is that radioactive isotope to date fossils and things like that. And here is normal carbon with atomic mass of 12. Now, what is atomic mass? One more time. That is, and probably not one more time, one of many times, are your protons plus your neutrons, the things inside the nucleus. So the atomic mass, the mass of the atom, is the nucleus. And so normal carbon's going to have an atomic mass of 12. And then C14, the radioactive isotope, it's still carbon, but it has an extra 2 neutrons. How do I know it's not protons? Because when you change the proton number, you actually change the element that you're talking about. And so cobalt also has a radioactive isotope, and these are all showing you different atomic masses. Hydrogen, as we mentioned, has an atomic mass of 1. There is a radioactive form of hydrogen. There's radioactive forms of iodine, iron, its mass, and what it's important for. Don't focus too much on types of isotopes, but do understand that isotopes are different forms of an element due to different numbers or varying numbers of neutrons found in the atomic nucleus. Another thing you're not going to focus too hard on are electron orbitals and shells. So orbitals are pathways that the electrons are going to rotate or move around the nucleus, and they represent how much space the electron is likely to be found. Okay, and so hydrogen's a very small atom with little space, and then we've got different sizes here of volume in which these electrons are likely to be found because they're constantly moving and they're teeny tiny, so we can't really watch them move. Now here is your periodic table of elements, and you might screenshot this picture and use this is a tool. This is like a hammer or a ruler or a computer. This I would not expect you to memorize, but this thing does help you out so much. For example, these numbers, numbering the columns, help you know how many electrons are already in the valence shell, the outermost shell. So how many valence electrons there are. And so For all of these elements in this column, they have one valence electron. All the elements in this column have two. Now you have to skip over here because these are like weirdos, but these all have three valence electrons. Carbon, which we just saw a minute ago, had four. Let's look back at that. 1, 2, 3, 4 in its outermost shell. Hydrogen just had one. So here's hydrogen in the first column, and here's carbon in the 1, 2, 3, 4 column. How many valence electrons does phosphorus have? If you said 5, you're right. What about chlorine? It's 7. Oxygen? 6. And then everything here, these are the noble gases. And they're noble because they are not reactive. They are perfectly fine in pure form because their outermost shells are full. Now, helium only has one shell. And if you'll remember, in that first shell, 2 electrons can be found. So helium has 2 valence electrons. And that's all. The rest of these are going to have 8 valence electrons because they have more than one shell. Now, let me just remind you, the first shell can only hold 2. So helium only has one shell, and it's a noble gas because its outermost shell, the only one it has, is full, where everything else has more than one shell and needs 8 valence electrons to become stable. And that is who you'll find here. A molecule is a chemical substance that is a combination of 2 or more atoms. So we've got O2 or N2. Water, H2O, is also a molecule. Glucose is also a molecule because a molecule is just anything that you bond together made of more than one atom. A compound is a type of molecule, but it's going to have different elements in it. So oxygen is a molecule, but it's not a compound because it's only made of oxygen atoms. Water is a molecule, and it's also a compound molecule because it's made of not just oxygen, but also hydrogen. Nitrogen is a molecule, but it is not a compound because it is only made of nitrogen atoms. Glucose, or C6H12O6, is a compound because it is made of more than one type of atom, and it is also a molecule because it's made of more than one atom. Now, chemical bonds are going to result when these atoms share, donate, or accept these electrons. And we're talking about the electrons in the outermost shell, these valence electrons. And so valence is the number of electrons in that outermost shell of any element. And that, as we've already mentioned, tells you how reactive they are. If the valence energy level is complete, it will not be reactive. If it only has, one valence electron to give away, to lose, or to gain, it's going to be very reactive because it's super desperate. It's so close to being stable that it's pretty desperate to become stable, where carbon is it's got 4, so it's not close to being stable at all, and so it's not as desperate, we'll find out. So there are many types of quote-unquote bonding, as we're going to use the term. And the ones we're going to really focus on are covalent bonds, ionic bonds, and hydrogen bonds. And in chemistry, they don't always call them hydrogen bonds, but for this course, we're going to use that term. So a covalent bond happens when 2 atoms share each a valence electron. And so if you look, this atom is kind of making a deal, if you will, with this other atom. And it says, hey, I'll let you use my electron if and only if you let me use yours. And what happens now is this electron has its own and this guy's, and same goes for the other atom. And so they're becoming more stable by sharing valence electrons. So look at the term covalent. Co, together, sharing, valence electrons. They are sharing valence electrons. Now, this would form what's called a single bond because we're only sharing one pair of valence electrons. So this would be like hydrogen. Hydrogen has one valence electron, other hydrogens only have one valence electron, and because they only have one shell, they need two to become stable. So what will they do? They'll share. And now this atom has 1, 2. And so it's stable, and this atom has 1, 2, and it's stable. And now we have H2 gas, hydrogen gas, a very non-reactive molecule. Is this a compound? No, because it's made of the same atom. An ionic bond is where one atom has one electron and another has, and it would benefit or become stable to lose that electron, and another atom would benefit to gain. So if it lost this electron, its outermost energy level would be full because this energy level would totally go away. This one is super close to becoming stable, and so it would accept an electron. I really don't love these pictures, honestly. But because this atom donated an electron, electrons have what charge? Negative. So because it lost its negative electron, it becomes positively charged. I think about if you lose a negative attitude, you have a positive attitude. And then if you gain a negative thing, if you gain a negative attitude, you will become negative. And so those are illustrations of ionic bonds. Now, hydrogen bonds are attractions between partially charged atoms and other partially charged atoms. And what we find is positive charges are attracted to negative charges. So if you have one molecule over here that has a slight positive charge, it will be attracted to the negative ends of other charged molecules. And so we'll look at these a little bit closer now. So as we mentioned, covalent bonds are formed when atoms share their electrons. So they're not donating and they're not receiving electrons, they're sharing. Covalent. A single covalent bond is sharing a pair of electrons. So think about a handshake. When you shake someone's hand, you're sharing one hand and they're sharing one hand. So it's a pair of hands forming that bond. A double covalent bond would be if you shook with both hands. So you're going to share 2 electrons and you have 2 pairs of electrons being shared. And those are going to be much stronger, of course, than a single bond. And so here's better examples, better pictures of this. So this is the one I was thinking about. This hydrogen just needs one more hydrogen electron to become stable, and so it'll share with another, and that's a single covalent bond. This right here. Now that's going to be shown as a line, okay? So HH single bond is just going to be a line between those. In a double covalent bond, so this looks like oxygen. It has 1, 2, 3, 4, 5, 6 valence electrons, and it needs 8 to be stable. So it will share 2 of its valence electrons with the other oxygen atom, and they'll become a molecule of oxygen, a stable, this is what you breathe, right? Another example of covalent bonds is methane gas. Probably it is the most simple organic molecule, methane. And so we have carbon here at the central with 4 valence electrons, but it needs 8. So it's going to share those and form single covalent bonds with 4 hydrogens, and you end up with methane, which is CH4. Now, all of these are considered non-polar molecules, and a polar molecule is when a molecule is formed that have different electronegativities, and electronegativity is just the ability to attract electrons. So as we saw here, all of these molecules have similar electronegativities, and so they're nonpolar. But in this picture, we have a water molecule. Water is polar. And the reason that it's polar is because oxygen has a whole lot of protons in its nucleus, which attracts electrons. Remember that negative things are attracted to positive things. So the electrons shift and really want to be over on one side of the molecule near the oxygen. So what it does is it makes the oxygen side of the water molecule slightly negatively charged. And the hydrogens, they're not losing their electrons, but the electrons are really wanting to hang out closer to oxygen. So because electrons are negative and they're shifting over to this side of the molecule, this side's negative and then this side's positive. And now we have a polar molecule. And remember, we looked at hydrogen bonds. This is going to be attraction between positive ends and negative ends of different molecules. So we have molecule A and molecule B here. So this could be a water molecule, and also this could. And the positive end of one water molecule could be attracted to the negative end of another water molecule. Now, ionic bonds are when electrons are transferred. So we have the donation and acceptance of electrons between two atoms. And these electrons are transferred, and I think of like somebody's stealing electrons, somebody's giving away. It's all about me, myself, and ionic. I don't know, but you got to come up with ways to remember this stuff. I have a weird brain, so I think maybe you have a weird brain too. So some of my stuff will help you. But when sodium, let's look at the sodium atom. Naturally, I'm going to go back to our periodic table and find sodium. It's way down here, okay? So it's in the first column. And let's go ahead and look at chlorine, which they're also going to illustrate. Chlorine's over here in column number 17. So it's going to have 7 valence electrons. This is sodium has 1 and chlorine has 7. Okay, let's go back to this. So here's sodium with that 1 valence electron. Now, to become stable, sodium either has to steal 7 valence electrons or get rid of 1. Which sounds easier, right? Getting rid of 1 electron would be so much easier. And it's so close to becoming stable that it's highly reactive. It's desperate to get rid of this 1 electron. And so it does. It will give force upon this electron, anyone who will take it. And chlorine, it had the valence number of 7, right? Let's count. 1, 2, 3, 4, 5, 6, 7. So it has 7 valence electrons. To become stable, it has to get rid of all of those or just get 1. And it's so close to being stable that it's desperate to receive 1. So sodium and chlorine work really well together. Something kind of interesting about sodium, it is so desperate to lose an electron, it'll force that upon things. And for example, when you mix sodium and water together, you have a huge explosion. It will kill you. You do not have access to pure sodium, my friend. Chlorine, which pure chlorine exists as a gas, and it is so reactive, it's going to steal electrons. If you breathe chlorine gas, you're going to die because it's going to steal electrons from you, friend. So these two things are super, super deadly. But when you get them close to each other, they have a perfect relationship, right? Sodium wants to give 1, chlorine wants to get 1, and so they do. And what happens is when sodium releases this negativity, it becomes positive. And chlorine, because it gained that electron, that negative electron, it becomes negative. And now those are attracted to one another. And this structure right here forms salt. It's delicious. Who knew? So two things that can kill you become delicious due to chemistry. Thank goodness for chemistry. Ionization is the formation of these charged particles when a molecule is formed by ionic bonds and it dissolves in a solvent. For example, this salt, if you put it in water, it's going to ionize in water. So these cations, which are the positive charge ions, so that would be the sodiums. The little green sodiums are all the cations. Cations have a positive charge. If you write the word out, cation, right in the middle of that word, you have a positive sign. The T looks like a positive, and anions are negatively charged ions, and they are attracted to each other. And an electrolyte is something like a salt or an acid or a base that when you put them in water, they disassociate. So if you put this salt crystal in water, these would spread out from each other and come back and spread out, and they're releasing these ions in the water. And so here is a picture of that, this salt crystal, these sodium and chlorides, delicious stuff coming in water, they can disassociate. Now, why are they doing that? Because water is a polar molecule, and it has a positive charge side and a negative charge side. And so these ions are going to disassociate and be attracted to those water molecules. So you can kind of see a water molecule here, and the chlorines are going to be kind of attracted to the hydrogens, and the sodium is going to be attracted to the oxygen. Now, liquids are in constant motion, so some of these chlorines will become attracted to a sodium and then disassociate again. So they're just constantly moving around, and all the positives are kind of trying to find anything that's negative to get next to, and vice versa. So when we say a hydrogen bond, this is going to be this attraction between these opposite charges of nearby atoms. And so it is a super weak bond that forms between hydrogens of one molecule and either oxygen or nitrogen of a different molecule. And it's so weak that it's often disrupted and temporary. And in chemistry, they're going to talk about van der Waals forces. And these are just weak attractions between molecules that show polarity. And hydrogen bonding is a van der Waals force. These neighboring groups with these slight attractions will interact and remain associated with each other. And so when you put a cup of water, when you have a cup of water, all those water molecules, which are polar, they have the slight negative and the slight positive ends of one molecule. They're going to be attracted to other molecules. You see this if you put drops on a penny, and you can see that surface tension. That's hydrogen bonding of water. It's kind of sticking to other water molecules. Another great example I love is when you are like driving in the rain and you are daydreaming out of the window and you see a water droplet moving down the window, and it gets really close to another water droplet, and those come together. That's because water molecules are attracted to other water molecules, and that is due to hydrogen bonding. Molecular formulas are going to show what atoms are in the molecule using the symbols and the amount of those elements involved. And those are going to be written as a subscript. So this is going to be a test question for you that you need to be able to see a molecular formula and know what is in that molecule. So for example, CO2, there is no subscript on the C, so that's telling you there's just one. And O2 tells you there's two oxygens. So the number that the subscript is hanging off of is describing the number of that element. H2O, how many hydrogens? And how many oxygens? I hope you said there's two hydrogens and one oxygen. Okay, glucose, C6H12O6. How many hydrogens are in glucose? 12. There's 12 hydrogens in glucose. This is great to know, but it really doesn't show the position of the bonds. And so you can kind of look at some of these things. So this is hydrogen and oxygen. These are both stable gases because they've reacted. Look at the single bond, the double bond between the oxygen. Here's water. And so you can see in its structural formula um, that it's got this bent shape and it's polar. CO2 has two double bonds in CO2, one carbon and two oxygens. And here's that methane gas we mentioned earlier, one carbon with four hydrogens, all sharing a covalent bond. And then you have C6H12 and C6H6 forming these carbon rings. And I want to teach you a little bit of a trick here. When, this is a pain in the butt to draw for chemists and to draw all these carbons and all these hydrogens. And so often what they'll do is they'll just draw these little stick figures, these rings here, and where every corner is going to represent the number of carbons in that molecule. And what trend you'll see is usually, carbon always has to have four bonds to become stable, four covalent bonds. So this carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. And so these carbons, this corner is a carbon, this corner is a carbon, so it's attached by a bond there. And then we're not drawing all the hydrogens around. Carbon is always associated with hydrogen in organic molecules. And so here, this is showing the double bonds between the carbons, and so that there's half the number of hydrogens because you already have extra bonding to help stabilize these molecules. And here's the space filling picture of some of these. So this is water, this is CO2, and this is C6H12O6. We have to talk about reactants and products when we talk about chemistry because the reactants are the molecules that are starting the chemical reaction, and the products are what are created or left after a chemical reaction. They are produced. And so we have a number of types of chemical reactions. There's synthesis reactions where we take two smaller, simpler atoms or molecules and combine them for a more complex. So the word synthesis means to create or build. So we're building something bigger. And so who are the reactants in this chemical reaction? Well, sulfur and oxygen are the reactants, and this SO2 is the product of that reactant. In decomposition reactions, we're actually going the opposite way. These are when bonds on a single reactant molecule are permanently broken into smaller, less complex molecules. And so we have two hydrogen peroxides, two H2O2s, and those bonds are being broken down into two water molecules and an oxygen molecule. Now, this is the first time you're seeing numbers in front of a molecule, and that's telling you how many of this one molecule. So H2O2 is hydrogen peroxide. And when you put a 2 in front of all of that, it's kind of like math, it factors through. So this is two hydrogen peroxides, H2O is water, and we have two H2O, so two water molecules and the oxygen molecule. We have exchange reactions where reactants are going to trade positions with each other and they release products that are new combinations of the two. So AB and XY is at the beginning of the reactant. Sorry, this should be an arrow. And we just trade. So we end up with AX and BY. So an exchange reaction. And a lot of times these are reversible reactions, so they can actually go this way, and here's your product, or these can be the reactants and go backwards. A catalyst in chemistry is some substance that's going to speed up this chemical reaction. And it's not going to be a part of the reaction, but it helps the reaction happen faster. So it increases the rate. And what we'll talk about quite a bit is enzymes. And enzymes are biological catalysts. So these are natural chemicals in cells that speed up chemical reactions. A solution is a mixture of one or more substances that can't be separated by filtering or allowing things to settle. So I'm thinking about salt water, sugar water, or tea. A solute is the substance that is dispersed in the solvent, which is whatever is doing the dissolving. So water is the most common solvent that we think about in nature. And when we say the word concentration, this is how much solute is dissolved in the solvent. So let's use tea, for example. If you have really strong tea, it has more tea leaf particles in water than a diluted tea. Or a super sweet tea has way more sugar dissolved in the solvent than a lesser sweet tea, which has less solute in that solvent. And you can actually calculate this by weight, how much solvent's there, how much volume is there, or a percentage. So remember that water is polar, and that allows it to form hydrogen bonds with other polar molecules. Ionic solvents dissolve because those cations are attracted to the negative poles of water, and anions are attracted to the positive poles. So each ion actually becomes hydrated. So it's interacting with water. So here you see sodium with all the negatives of the negative ends of water attracting to the sodium, and chlorine attracting the positive ends. When we describe something as hydrophilic, hydro, that prefix means water. Philic, phil, means love or attraction. I've seen this with the word Philadelphia. It's the city of brotherly what? Do you know? Love. I actually lived there for a year. They aren't very lovely, by the way. But Philadelphia means brotherly love. Hydrophilic means the love or attraction of water. I also help myself remember that if you think about like Dr. Phil, he's tough love or something. So hydrophilic is love or attraction. So a hydrophilic molecule is one like sugar and salt that attract water to their surface. And then hydrophobic is the opposite. So hydro means what? Water. And what's a phobia? It's a fear of something. So hydrophobic substances are really, they're not afraid of water, but they don't mix with water because water is polar and hydrophobic molecules are nonpolar. And things that are polar only mix with other polar things. So benzene, that ring that we saw, repels water. Oils are going to repel water. Why? Because all lipids are nonpolar and therefore hydrophobic. There are a few molecules we'll talk about. I'm thinking of two right off the top of my head that are amphipathic, maybe three actually. Amphipathic molecules have both a hydrophilic end and a hydrophobic side or properties, the same molecule. And phospholipids are a very popular example of that, where the phosphate head is hydrophilic and the lipid tails are hydrophobic. Soap is amphipathic. That's why it's able to cut grease and get it to wash down. If you've ever had a pan, you've cooked some meat or whatever, you ate your meal, you go back and the grease is there in the pan, you don't just rinse that off. It won't come off. Why? Because water's polar and the grease is non-polar. Water is polar and the grease is non-polar. The grease is hydro what? Phobic. So it doesn't mix with water. So what do? You put soap on it, which is slightly hydrophilic and slightly hydrophobic, and that's how it's able to form that grease into blobs. Cholesterol is another molecule that is amphipathic. And we'll talk a little bit about the pH scale, and I think we need to take a break, right? So let's talk about pH. An acidic solution occurs when something in the water releases hydrogen ions. So you're going to see a lot of hydrogen ions. And anytime you have hydrogen ions in a solution, we're going to call that acidic. Okay. Basic solutions occurs when whatever's in the water releases excess hydroxyl ions or accepts hydrogens. And so basic solutions are going to have a lot of OH ions in them. And so this is showing the pH scale in moles of liters of hydrogen ion, and it's represented by a log. And the easy way to know about this is the pH scale you've probably heard of, going 0 to actually 14 for us in biology. And these numbers are a little off because of my computer when I use this picture. But what is interesting, this is going to show the log of hydrogens, and this one's showing the log of hydroxides. And so I want you to look at a pH of 7, and it's shifted. So 1, 2, 3, or 0, 1, 2, 3, 4, 5, 6, 7. Look at this. At a pH of 7, there is 10 to the negative 7 hydroxides or hydroxyl ions, and there's also 10 to the negative 7 hydrogen ions. And so because these are even, they are neither an acid or a base. Let's see. This is what I want to show you. That 10 to the negative 7 is where you have even amounts of hydrogen and hydroxide ions. So if you'll think about this pH scale like a teeter-totter or a seesaw, if you have even number of hydrogens in the solution as hydroxides, they actually are attracted together and form H2O, water. And so distilled water is a 7.0 on the pH scale. As you start to add more and more hydrogens, though, what's going to happen to our seesaw? Well, this is going to become heavier, and so we're going to actually move this way. So as you move further from 7 down the pH scale, you're becoming what? More acidic. So yogurt is a pretty weak acid compared to lemon juice, which is a very strong acid. The lower the number, the more acidic. And anything below 7, like milk, is an acid. Okay, 7 is neutral because it has both even numbers of hydrogens and hydroxides making water. All right. How much stronger of an acid is 5 than 6? Well, what's interesting, even though this is just one step on our pH scale, this pH of 5 is 10 times the strength. And we can see that using this math here, that this is 10 times the strength every step we take. And so how much stronger is 4 than 6? Well, it's 2 steps. So a lot of students mess up and tell me the wrong answer. How much stronger is 4 than 6? Well, if 5 is 10 times stronger than 6, 4 is 100 times stronger. It's 10 times 10 times. So that's 100 times. We're not adding these together. They are times. Okay. So what about 3 compared to 6? Well, 5 is 10 times stronger. 4 is 100 times stronger. 3 would be 1,000 times stronger. Wow, just keep adding zeros. All right, that's what I want to tell you about acids. Now, acids usually taste sour, and bases are usually going to be like slippery things. I don't know that I would have tasted them, but in our previous example with acids, we added hydrogen ions. Well, this time let's go back to neutral where we have even amounts and add more hydroxide ions. What's our seesaw going to do? It's going to go there's going to be more on this side, so it's going to go that direction. So now we're moving away from 7 in this way, and we're getting more alkaline, more basic. This is a very strong base. And I will tell you, both acids and bases can burn you, are toxic to you. So you want to be careful with both. Most people just think about acids like hydrochloric acid burning you. Potassium hydroxide will also. Oven cleaner, you're going to wear, you don't want to breathe that stuff in, and you definitely are wearing gloves. So just FYI, acids and bases are both dangerous depending on their strength, and the further you get away from 7 on the pH scale, the stronger they are. Now, what makes a base so strong? Because it has all these hydroxide ions. And so here are some things that are common bases you may have heard of. Now, what happens, so anything, once again, below a 7 is acidic, and anything above a 7 is basic. So the higher the pH scale, the more basic something is, the lower the pH on the pH scale, the more acidic something is. Reactions where acids react with bases do result in water. They neutralize. And so think about having, if you have 15 hydroxide and 15 hydrogens, they would be even. They would neutralize when you mix them together. And they end up with salt. So here you have hydrochloric acid and sodium hydroxide, hydrochloric acid, sodium hydroxide base. And when you mix these together, you get water and sodium chloride, our table salt we've already talked about. So we're going to stop here, take a break, have a snack, reward yourself for watching this video, maybe do some of your homework or some of your labs, and then we'll finish up this chapter talking about biochemistry, the chemistry of carbon, and organic chemistry.